So I say, following common superstition, it's a superstition until you can prove it. But it is a theorem, okay? So it's a superstition, a theorem's a superstition until you can prove it, but you accept it anyway. Okay? It's not really a superstition, I'm using hyperbole here. Okay? Okay, so superstition, okay, theorem. We get the transition matrix by reducing an augmented matrix, right? Okay? So, the augmented matrix is the matrix that has the columns of one basis and the columns consisting of the vectors in the other basis. It actually doesn't matter which way we do it, which way you write it down. I think I got that written down backwards from the way the theorem states it. Okay? We get the matrix for a similarity transformation. And that might be P or P inverse. I'll let you think about it. Okay? When we do that, we get a matrix that has the same eigenvalues, has the same determinant. Okay? Well, when we do then your P inverse AP matrix, and I'm not sure if this should be P or P inverse, I have to write it out. Okay? And you can get that straight. Okay? So I'm going to say, is this P, or is this what we call P inverse? Well, it's going to be P inverse AP, and it's P here or P inverse here, according to which one does the job right. Okay? The matrix you got here transforms what to what, and I want you to think that through. Not because I don't want to think it through, okay? But I want to take time to think it through right now, and I'm going to rely on you to do that, okay? The point is, this is going to be the matrix with respect to the standard basis. Okay? And when you multiply it by 2, 1, negative 5, you're going to get 1, 1/2, negative 5/2. And when you multiply it by 3, 2, 4, you're going to get 6, 4, 8. You're going to multiply these by 2, 1/2, and these by 2, and this is going to be negative 6, negative 5, 3. Okay? There are many other things that are so about this matrix, and they may be a little surprising. Okay? The determinant is the same as the determinant of this matrix. In this case, the determinant's negative 1. Because, of course, you multiply these diagonal elements real easily, right? That tells us things about volumes and a lot of other stuff. That's easy to prove. Because the determinant of P inverse is the reciprocal of the determinant of P. This is one of the properties of determinants that you've known for quite a while now. And the determinant of the product of the three matrices is just the determinant of this times the determinant of this times the determinant of this, right? So it's a reciprocal of the determinant of P times the determinant of A times the determinant of P, which just gives you the determinant of A, right? So if the determinant of P is 4, then the determinant here is 1/4. The determinant here is 4, right? 1/4 times whatever the determinant of A is times 4 gives you the determinant of A, right? Okay, so that's very easy to understand. If you understand the properties of determinants, it could hopefully prove some of them. Has other properties that I'm going to ask you to verify, okay? I'm going to probably ask you to go ahead and invert this and do this. The trace of the matrix is invariant under similarity transformation. Know what the trace is? It's the sum of the diagonal elements. So when you do this and multiply it out, your diagonal elements are going to add up to the same thing. Many other connections, okay? So this is kind of a big deal. And the other part of the big deal is, of course, we're working backwards from the eigenvectors and eigenvalues to the matrix, to the representation in terms of the standard basis, okay? When you have a representation in terms of a standard basis or some other basis, if you have three distinct eigenvalues, real eigenvalues, you can diagonalize the matrix. In other words, this transformation will diagonalize the matrix. Okay? And actually, I think I've got these backwards because P inverse AP is the one that takes you from standard basis to the eigenvector basis. Okay? But work out the details of that and understand why it is what it is. Okay? I could stop and explain it, but I'm not going to take time to do that. I want you to think it through. Now, you can always memorize. That's what you do if you don't understand it completely. And you know, I don't expect everybody to understand every proof and every nuance in this course completely. Okay, there's some important ones that I do want you to understand. So at some point, you just got to memorize things, but try to keep that number, the core of things you got to memorize because you can't put them together completely, as small as possible. Because the smaller nucleus of things you need, and the bigger your ability to put things together. Okay, and the less you've got to, less memory you've got to carry into a situation. That varies from one person to another. How much of that you got to use. I keep encouraging people that way, though. Okay, very good.